In 1925, Erwin Schrödinger is searching for a wave equation that governs the behavior of quantum particles, building on de Broglie's insight that matter consists of waves. He comes up with one of the most important and famous equations in all of physics, the Schrödinger equation, and featured prominently within it is I, the square root of -1. While mathematicians have grown accustomed to imaginary numbers, physicists have not, and are uncomfortable seeing it show up in such a fundamental theory. Schrödinger himself writes, "What is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. The wave function psi is surely fundamentally a real function. This seems like a fair objection, so why does an imaginary number that first appeared in the solution to the cubic turn up in fundamental physics? Well, it's because of some unique properties of imaginary numbers. Imaginary numbers exist on a dimension perpendicular to the real number line. Together, they form the complex plane. Watch what happens when we repeatedly multiply by I. Starting with 1, 1 times I is I times I is -1, by definition. -1 times I is -I, and -I times I is 1. We've come back to where we started, and if we keep multiplying by I, the point will keep rotating around. So when you're multiplying by I, what you're really doing is rotating by 90 degrees in the complex plane. Now, there is a function that repeatedly multiplies by I as you go down the x-axis, and that is e to the ix. It creates a spiral by essentially spreading out these rotations all along the x-axis. If you look at the real part of this spiral, it's a cosine wave. And if you look at the imaginary part, it's a sine wave. The two quintessential functions that describe waves are both contained in e to the ix. So when Schrödinger goes to write down a wave equation, he naturally assumes that the solutions to his equation will look something like e to the ix, specifically e to the ikx minus omega t. You might wonder why he would use that formulation and not just a simple sine wave, but the exponential has some useful properties. If you take the derivative with respect to position or time, that derivative is proportional to the original function itself. And that's not true if you use the sine function, whose derivative is cosine. Plus, since the Schrödinger equation is linear, you can add together an arbitrary number of solutions of this form, creating any sort of wave shape you like, and it too will be a solution to Schrödinger's equation. The physicist Freeman Dyson later writes, "Schrödinger put the square root of -1 into the equation, and suddenly it made sense. Suddenly it became a wave equation instead of a heat conduction equation. And Schrödinger found, to his delight, that the equation has solutions corresponding to the quantized orbits in the Bohr model of the atom. It turns out that the Schrödinger equation describes correctly everything we know about the behavior of atoms. It is the basis of all of chemistry and most of physics. And that square root of -1 means that nature works with complex numbers and not with real numbers." This discovery came as a complete surprise to Schrödinger as well as to everybody else. So imaginary numbers, discovered as a quirky intermediate step on the way to solving the cubic, turn out to be fundamental to our description of reality. Only by giving up math's connection to reality could it guide us to a deeper truth about the way the universe works.